Okay, it's me again. Something completely different. Exploratory work, so don't shoot the pianist too quickly. Inverse problems. To summary, a summary is that they are everywhere. To multiply is easy, to divide is difficult, to derive is easy, to integrate is difficult, etc., etc. And it's probably the most frequent problems in experimental physics. You want to retrieve something, and observation results from several integrations of an unknown distribution. And you know, in geophysics, seismology, oceanography, everywhere, you have this kind of problems with mostly radial symmetry and mostly also a complex forward model. Probably many of you have met methods to inverse Bayesian, Phillips-Toomey, Levenberg-Marquardt, Shine, etc., Bacchus-Gilbert, etc., etc. I want to have a look here at a different point of view, is that if you have to process a large number of observations, then what is the total computational cost of your inversion, of your processing? And you could have a proxy that could be how many calls do you have to do to the forward model. And as many of these forward models are nonlinear, you almost automatically you have to face iterative methods, except in trivial analytical case. For instance, in ALTIUS, when we increase this number of principal components, we see that the Levenberg-Marquardt algorithm that is optimizing the solution takes more and more in a polynomial, more and more calls to the forward model in a quite polynomial, certainly not linear. And even worse, all intermediate steps, when you look to the solution, are intermediate. The path to converge is a priori unknown. And mostly, if you compute Jacobians, whatever, you don't record the function calls. So actually, they are useless. You are just interested by the solution. So it's there is some waste of calls to the forward model. And you should consider also that with respect to what I call a big training set, so a huge ensemble of forward model simulations to check whether it's cheaper or not with respect to a global processing. So inverse problem, you have a forward model that translate the state vector into your observation, radiance, transmittance, whatever. And what I will call a direct inversion is very simple. You just swap the blue and the green boxes. You replace your forward model by, let's say, a black box. And what you have to do now is for this big training set to constrain the black box, to compute it in such a way that the green box will be predicted from the blue box. Okay, this is the direct inversion as seen here. And I would say this is, in my opinion, fresh science. I saw this paper about MLS, application of machine learning for MLS. I think we have a poster about that. I have seen different talks and presentations about the use of machine learning here. And I will focus directly on a concrete example that is stratospheric aerosol in bright limb. It's related to what we do in ALTIUS, but not only, it is a general approach. I have some assumptions. I will use effective log normal unimodal with a mode radius, a sigma, the distribution width, and a number density profile. I assume that the refractive index is known at 1.4, 1.46, and our big training set will consist, actually it is the same that was used to build the lookup table for ALTIUS this morning. It's about 25,000 cases where, for any case, it's any ozone, any air, any aerosol number density profile, random, any geometry solar geometry in solar zenith angle and solar azimuth angle, any particle, effective particle size between 0 and 600 nanometer, any sigma between 1.2, 1.8, any albedo between 0 and 1. We compute those vectors, we use mi-scattering code, and we predict the radiance at 8 wavelengths. Okay, so on the left side you have the you have the ozone profile of the big training set. Here you have the aerosol number density profile. This is air, and the 3 Stokes vector at 8 wavelength. You see them here as a function of altitude, and you see the spread corresponding to the domain we are exploring with this BTS. Are we able to retrieve particle size distribution and number density? It's an important question, of course, in general, and also due to possible interference in some cases with ozone retrievals. And my answer is at first sight, yes, because if I select the ensemble of radiances according to very small, mid-size, and big-size particles, you see at different altitude, you see the change of the slope of the spectral radiance. This is the Rayleigh limit for extremely small particles, and you clearly see, at least for the effective radius, a nice dependence. So in general, some time ago I tried to use a chromatic method, playing with the ratio of extinction coefficient of, more exactly, extinction of ratio of extinction coefficient at two wavelength 5 to 5 with respect to 600 and 675 with. So these two ratios in single scattering at least, there are, you factorize the number density and you have a pure chromatic or spectral information. So there is a relationship between the effective radius and the distribution width and the two ratios. And then the first tentative was to use six radiance channel and to correlate them to the rho 1 and rho 2 and then to the effective radius and the sigma. And this was the result that, of course, we know in the BTS the true effective radius we put, and this is the retrieved one by the method, and certainly a valid regression here, not perfect. And for sigma, a little bit disappointing because you see a regression, but it's not very accurate. So now we have an improvement of this method, which is called ANI, Aerosol Neural Network Inversion. And there are three key concepts. The first is to think what is the information content of the observation profile. What the signal is a profile, a radiance profile. How many degrees of freedom does it contain? And you can do that by the usual way. You have a big ensemble, you have a covariance matrix, you can produce a PCR analysis, and you can reanalyze the radiance profile according to that. So for our A channel from the UV to the infrared, if you want to reconstruct at 0.01% level the profile, the radiance profile, it's enough to have 5 components in the UV, and it increases because we have more and more aerosol influence up to 16. But it's a serious compression of the total number of radiance we have computed, because it was 248, 8 times 31, and we have now 91 degrees of freedom for this accuracy level. The second key concept is you will build a normalized radiance vector where you will pile up the coefficient of the UV channel, then the visible, etc. And you add the solar angles for, let's say, to inform the system about the geometry. You may also have, I have not so much time to discuss sensitivity, but you can discover that the UV part is not contributing to the radiance enough. And if you would like to keep particles too small, you will find a bad regression between the target and the result, and this is this parasitic distribution here, which is associated with too small particles to be physically informative about their size. So we will select only particles of effective size greater than 100 nanometers, And we will do a mapping between, of course, this possibly 5 aerosol components, or the effective radius, or the sigma, and even the albedo to see what it gives. And you can try this in the usual way with a neural network. And really, it works better than a linear. If you use a linear relationship, you will get the blue distribution. With a neural network, you will be able to have the red one. Okay, this is the example how to retrieve independently the effective radius. You start with this normalized radius vector. You have not so deep network compressing information, and you predict for instance, the radius. This is the worst result. It is about albedo. Not so good, a regression, but you see an accuracy not better than 25–30%. This is normal in the case of ALTIUS because we renormalize the radiance. So this information is coming actually from the residual of the albedo removal. So this method says something about albedo, but not so much. Now this is the distribution width, and this is what we obtain, already a better regression. It's clear. Certainly compared to the chromatic first guess we had, and you see that here it's more accurate, something like 5%. And the best, it's not a surprise, result is obtained for the effective radius, where then the regression is very nice, more than 99%, and there is an improvement of factor 3 with respect to the first guess of the chromatic method. And by the way, why not to apply the method? No, I have to say something. Even I am short of time. If you remove the infrared channel, for instance, the 1 micron channel, your regression gets worse. So it proves that it's mandatory to use the near-infrared channel to extract the information about the particle size. I did the same for the log of the number density profile, this kind of mapping. And here also we have a regression which is about 15 to 20% on the log of the densities, which is about 20% on the densities. And this is typical example of profile that we retrieve of the number density, not always perfect, but mostly satisfactory within 20%. And the error is spread rather uniformly between 0 and 50 kilometers. Again, well, and I see I will not have time to discuss example, but I want to insist that is this method robust with respect to experimental noise? And the answer is yes, because in this example I retrieve an aerosol number density profile with an excellent signal-to-noise ratio. I degrade it by a factor 4, by a factor 4, by a factor 4. You see that down to 100 for signal-to-noise ratio, we are still we have some acceptable results, and it starts to degrade here. So why is the method rather robust? It is also a bonus that the fact that at the input we use a description in terms of principal component analysis of the radiance. In other words, for instance, if you make a Fourier analysis of the signal of the radiance profile contaminated by 4% of Gaussian noise, you have the red curve. And when you reconstruct this radiance profile with 13 components, you get the green curve, which is actually a strong filtering of the noise, and a quite natural filtering because it is using the PCR. 2 minutes almost? Okay. There was this interesting paper 2 months ago about retrieval of number density and particle size distribution. Okay, I had a quick and not yet consolidated comparison. At least for effective radius, it's satisfactory, and in our model it is an assumption, it's constant, and a posteriori this assumption is not so bad with respect to Ohms and Sage at different scattering angle. I don't want to comment number density because it's less satisfactory. Albedo also is just to try to recognize a planetary albedo. It's possible even if the accuracy is not good, and this is probably the last and very fresh results. This is Onga Tonga. I have processed OMS data in this latitude band. And yes, I was first happy to see a nice increase of the particle size distribution of the effective radius. But actually, it was also present in 2021. So then I realized, by looking at the results published by the group of Alex, that in Skiamaki they had seen also this seasonal effect in the effective radius. And then I have superimposed the 2 years, 2022 and 2021, and Onga Tonga is that and that before remerging of the curve. These are the climatology produced by this Skiamaki paper. So we see an effect, but not so dramatic. Voilà. I will not comment number density. A preliminary summary of this ANI method. Aerosol can be retrieved, in my opinion, in limb geometry, and it can be retrieved independently of ozone and air, because the neural network doesn't know anything about ozone and air. It just processes radiance data. We expect an accuracy of 5% for particle size distribution, assuming log normal, of course, radius and width, and 20% for the luminosity. Albedo is anecdotic and should be improved on the absolute radiance. Conclusion about the generic method, which is not focused only on ALTIUS. It is possible to develop powerful direct inversion scheme. You need a big training set. You need to extract the information of this of the observation to reduce the size of the problem, and by the way, to also to define your resolution. Then you make a mapping of the normalized radiance vector for the interesting channels, and you feed a shallow or not so deep neural network. You have a bonus is that noise amplification is under control, and you don't need any regularization method. So ANI is ready to be consolidated. It's a lot of work, of course. And the method is generic, so it could be used for ozone, and I have already encouraging results, or any other secondary products in any geometry, limb, or occultation. That's it.